Hello and welcome to lesson number 21, Integration Part 1. Similar to how differentiation had multiple videos, integration is going to have multiple videos. Welcome to integration number 1. In this video, we are going to be discussing the basis of integration and the basic idea of it. And in the next video, we will be going further into concepts of integration. In order to start this video, we need knowledge on differentiation first. So therefore, if you haven't watched the video already, click this video in the top right and come back. However, you do not need any knowledge on integration, as that's what we will be establishing in this video. So then, moving forward, in differentiation, what we do when taking the derivative is this process here. We have some function which I have labeled as capital F of x, and we try to find another function simple of f of x, which gives the rate of change of the function capital F of x at any point x. In this thing which we are going to be calling indefinite integration, what we are doing is the inverse process. Due to this process is sometimes called taking the antiderivative. In indefinite integration, or I'll say /antiderivative, what we are thinking about is, given a function f of x, supposing that this function is the rate of change of a different function capital F of x, how do you find that function capital F of x? So here basically, in the first thing, in derivation, we have a function and we are asking what is the function that gives the rate of change of this function capital F of x. In integration, as in indefinite integration or taking the antiderivative, we are asking the opposite question. I have this function, I know it's the derivative of some other function, and I'm asking what is that other function to which this function I have, simple f of x, is the derivative of. For this thing, we know that there are multiple notations for taking the derivative. The most common one is to say d of capital F of x with respect to x equal to simple f of x. This is the notation corresponding to this process which we have in the first line here. The correspondent notation for this, for indefinite integration as in taking the antiderivative, is this notation here. We say that the integral of simple f of x with respect to x is equal to the capital F of x. Basically here we are saying that if we have that the derivative of capital F of x with respect to x is simple f of x, then doing the inverse, we can say that the integral of simple f of x with respect to x is capital F of x. So these two statements are identical to each other. They reflect themselves. Given that this is the case, the derivative of the capital F of x with respect to x is equal to simple f of x, then with this notation, the integral sign of simple f of x with respect to x is the capital F of x. Now then, this is not exactly true because there are other little subtleties that are happening here, and we will now discuss those subtleties. So basically, what I am suggesting here before we get to the subtleties is the fact that if we treat derivation as a kind of function where we take an input of capital F of x and produce an output of simple f of x, then integration or taking the antiderivative is kind of an inverse function, as in we take the input which was the output of the previous function simple f of x, we substitute as the input, and then we get the output of capital F of x. So we can think like this antiderivative, as in this integral, this indefinite integral, is a kind of inverse function to taking the derivative. However, as you may recall in your video on functions, inverse functions may not actually be proper functions. And what it means to be a proper function is that for one input, you only have one output. As we will be showing right now, this is not the case for indefinite integration. So then suppose we have the function y equals x squared and we want to take its derivative. Therefore, what we will have to do is take the derivative of x squared with respect to x. Recall on our rules on derivation, when you have something like this, all you have to do is take that power to the front and then raise x to that power minus 1. So therefore what we have here is 2 times x to the power of 2 minus 1, which is equal to 2 times x to the power of 1, or simply 2x. So therefore in this case, the derivative of this function here, x squared, is simply 2x. So therefore, when we have this format, we know that according to what we just showed up here, this means that the integral of 2x with respect to x must be x squared, because that's what we just defined here. We defined that if we have a function capital F of x and we take its derivative to be simple f of x, then when we do the inverse, we take simple f of x and turn it into capital F of x, i.e. if we take the derivative of a function and it's a different function, then when we take that function, integrate it, we should get back our original function. So here, according to that, we would expect that the integral of 2x with respect to x, as in this notation here, would be equal to x squared. However, if we instead consider, let's say, the derivative of y equals x squared plus 1, and we try to evaluate this thing, we know from our rules on derivatives that when we have something like this is just the derivative of the first thing plus the derivative of the second thing. The first thing's derivative is 2x as we just observed, and the second thing is just 1. The derivative of a constant with respect to x is 0, so this is going to be 2x plus 0, or simply 2x. So therefore, we have that the derivative of x squared plus 1 is equal to 2x. So according to what we established, this must mean that the integral of 2x with respect to x is equal to x squared plus 1. And now we can see we have two different answers for a single input. If we treated integration as a function or antiderivation as a function, we can see that a single input of 2x appears to be giving us two outputs of x squared and x squared plus 1. So then, which is it? Well, it's neither of them. If we do another one, we can see that the derivative of x squared plus 2 with respect to x, if we just consider this is the derivative of x squared, which is 2x, plus the derivative of 2, which is 0. So plus 0, which is going to be 2x. So therefore, we can see in this case as well, the integral of 2x with respect to x appears to be, in this case, x squared plus 2. We could do this with any constant we wanted. For example, for a little bit of a fun case, let's consider the derivative of x squared plus pi. In this case as well, if we take the derivative of x squared plus pi, this is going to be the derivative of x squared, which is 2x, plus the derivative of pi, which is 0. So 2x plus 0, which is going to be just 2x. So therefore, the integral of 2x in this case appears to be x squared plus pi. In fact, for any k, any constant k, the derivative of x squared plus k with respect to x is going to be equal to 2x, and therefore the integral of 2x with respect to x is going to be equal to x squared plus k for any k element of the real numbers. So now you might be wondering, well, if this could be literally anything, if there could be literally any constant on the front here, what's the point of it? Why this is not a function. We cannot give one particular answer if we ask for the integral. So what am I supposed to write here? Well, since we cannot give any particular answer, we give every single possible answer. And what I mean by that is, in this case, we know that the commonality here is this x squared. For every time we have a 2x and we integrate it, we know we are definitely going to get an x squared. What we don't know is the constant that we get in the front. So in indefinite integration, or taking the antiderivative, we say that the integral of 2x with respect to x, which is what we wanted to find, is equal to x squared plus, and by convention what we put here is a capital C, and then we say where capital C is an arbitrary constant. Basically to say there are a very large infinite family of functions whose derivative is going to be 2x. Therefore, if we take the integral of 2x, we have a very large family of functions, which is the answer. However, we can write that very large family simply as x squared plus c, where c is some constant. And again, we don't know what it is. C could be literally any number, but we know that it has to be some kind of constant. So we just say the integral of 2x dx is going to be x squared plus c, where c is some kind of constant. We don't know what it is, we don't claim to know what it is, we just say that it's some kind of constant. In fact, if you want to find this constant, you need some more information. The information we need is the value of the function at a particular point. For example, if I say that the derivative of capital F of x is equal to 2x plus 1, suppose I give you this information, we can, with this information, find a family of functions which capital F of x could be. However, if I give you this information and I also give you that f of, let's suppose, 0 is equal to 1, now we can use these two bits of information to find exactly what the function f of x is. So then, here, from this first bit of information, we know that f of x is equal to one of the integrals of 2x plus 1 with respect to x. From the second detail, we know that f of 0 is equal to 1. Now then, using these two, we can find exactly what the value of f of x is. Considering this first statement, we know that the integral of 2x plus 1 dx is equal to f of x. Considering the antiderivative idea, we need to find some kind of function whose derivative is equal to 2x plus 1. Consider x squared plus x. The derivative of x squared plus x with respect to x is going to be the derivative of x squared, which is 2x, plus the derivative of x, which is 1. So 2x plus 1. So therefore, from this we can say that the integral of 2x plus 1 dx is going to be x squared plus x, which is this bit, but then we also know that there could be any constant on the front, so therefore we need a plus c here. So therefore, f of x has to be the integral of 2x plus 1 with respect to x, which has to be x squared plus x plus some constant c, which we do not know. This is one bit of information. The second bit of information, f of 0 is now going to be handy here. From this we know that f of 0 must be, here substituting the 0 into these two, we have 0 squared plus this x is going to be 0, so plus 0 plus capital C is equal to f of 0, which we know is equal to 1. So therefore this is equal to 1. Therefore we get that c is equal to 1. Substituting this back into equation number 1, we can see that f of x must then be equal to x squared, so equal to x squared plus x, so plus x plus, and c in this case, from our evaluation of f of 0 equal to 1, we know that the constant c for this particular value of capital F of x must be equal to 1. So therefore we get that f of x is equal to x squared plus x plus 1. So then, the antiderivative is not a function, it gives you multiple answers for a single input, as in the plus c. However, if you want to find a particular one of the outputs, as in there is one particular function which we know is having certain properties, we can find some property of that function and use it to isolate what that function should be. In this case, we have the value of the function at 0, we know it's equal to 1. Using that, we can narrow down the infinite set of c's into just a single value of c. And that value of c is correspondent with capital F of x. So now let's look at some common rules and common integrals that we have within this subject. For some common rules of integration, what we're going to be doing is considering first a derivative. We know from derivative rules that the derivative of the function f of x plus the function g of x taken with respect to x is in fact equal to the derivative of the first function f of x plus the derivative of the second function g of x. So plus the derivative of g of x with respect to x. Similar to this, if we invert this process, we know that the integral of a sum of two functions, let's say f of x plus g of x taken with respect to x is equal to the sum of the first function f of x's integral with respect to x plus the integral of the second function g of x taken with respect to x. This is going to be our first rule. It is similar to the rule we have above for derivation, where the sum of two functions and we take its derivative is going to be the derivative of the first function plus the derivative of the second function. Similar to that, for integration, we have the rule that if we have a sum of two functions and we take its integral, it's equal to the integral of the first function time plus the integral of the second function. Similar to this, again, taking derivatives, we know that the derivative rule, if we have a constant times some function and we take its derivative, this is equal to the constant times the derivative of the function itself. Similar to this, integration has a rule where if you have an integral of a constant times a function, and we take that with respect to x, this is going to be equal to the constant times the integral of the function f of x taken with respect to x. So again we can see a kind of symmetry with the derivative rule as an integral rule. These two are the ones we are going to be covering for now. There are some more complicated integral rules which we will be covering in the second video. So for this first video on integration, we have these two rules. Using these two rules and the next bit, which is going to be some common integrals, we can solve most simple integrals. So then, for the simple integrals that we know, we are going to be using derivative identities because we are going to be using the idea of the antiderivative. So then, we know from our derivative rules that the derivative of x to the power of n taken with respect to x is going to be n times x to the power of n minus 1. Therefore, the integral of n times x to the power of n minus 1 taken with respect to x is going to be x to the power of n, but recall we need to add a c here because any set of functions x to the power of n plus c would result in their derivative being n times x to the power of n minus 1. So therefore, the integral of n times x to the power of n minus 1 with respect to x is going to be x to the power of n plus c. However, this is not the format that we usually write this in. Usually we rearrange things. Usually, using the second rule where we have constant times a function is going to be the constant times the integral of the function, we usually write this as n times the integral of x to the power of n minus 1 taken with respect to x being x to the power of n plus c. And then taking this n to the other side, we usually write this as the integral of x to the power of n minus 1 taken with respect to x being x to the power of n divided by n plus c divided by n. Now then, here, since c divided by n is just some other constant, we really don't care and we can actually redefine this as being some other constant. We'll just call it d for now, and we'll say that the integral of x to the power of n minus 1 taken with respect to x is going to be equal to x to the power of n divided by n plus c divided by n. However, once again, usually we don't write it in this format. Usually we want just some number on the top here. So let's replace n minus 1 with m. So let's suppose that n minus 1 is equal to m, which would mean that n would be equal to m plus 1. Therefore, what we have is that the integral of x to the power of m taken with respect to x is going to be x to the power of, here n is m plus 1, so we have m plus 1 divided by, and here n is m plus 1, so divide by m plus 1, plus this thing which is going to be c divided by m plus 1, and once again, since c divided by m plus 1 is just some other constant, we write this as some other constant, let's say d. So therefore, what we usually write is that the integral of x to the power of m taken with respect to x is going to be x to the power of m plus 1 divided by m plus 1 plus some constant d. Rewriting this in some more familiar symbols, we would usually not write this in terms of m and d. We would usually write that x to the power of n dx is equal to x to the power of n plus 1 divided by n plus 1 plus some integral constant c. This is what we write. This is a common integral. In fact, it's probably the most common integral, the simplest integral that we have. It is that the integral of x to the power of n, or some integer power of x, is going to be x to the power of n plus 1 divided by n plus 1 plus c. Now this does extend for non-integers as well, and this also only works for n not equal to negative 1. You can see why that would be the case. When n is equal to negative 1, something else happens, and we can see in this expression that we currently have, when n is equal to negative 1, we get a divide by 0 on the denominator. This is in fact not what happens. Something else happens when n is equal to negative 1, which we will be discussing. But for now, we can see here, for x to the power of n, where n is some real number that's not equal to negative 1, its integral is going to be x to the power of n plus 1 divided by n plus 1 plus some constant c. So we're going to write this as our first simple integral. This integral was gotten by considering derivatives first, and considering the idea that an integral is basically the antiderivative, at least for now. So then, moving forward, let's now consider the next integral, which is actually going to be dealing with the case where n is equal to negative 1. When n is equal to negative 1, we have the integral of x to the power of negative 1 or 1 divided by x taken with respect to x, and we want to find what this is equal to. So then, what we know in terms of derivatives is that the derivative of the natural logarithm of x taken with respect to x is equal to 1 divided by x. So therefore we would think that the integral of 1 divided by x taken with respect to x would be just the natural logarithm of x plus c. However, there is a subtlety to take in here. The natural logarithm of x, or any logarithm function for that matter, within the real numbers is only defined for x being a positive number. Therefore, this is only defined for x being greater than 0. However, 1 divided by x is defined for x's that are less than 0 as well. In fact, 1 divided by x is defined for all x's elements of the real numbers except at the point x equals 0. So then, what we need to do actually is to consider not only this case, but rather the case where x could be negative. In this case, the natural logarithm is in fact going to be the answer for x's which are greater than 0. However, for x's less than 0, we need to have a different approach. To do that, let's consider the logarithm of negative x for x's which are less than 0. And let's take the derivative of the logarithm of negative x with respect to x for x's less than 0. So actually here I've missed the x here, for x less than 0. So then, for x's less than 0, negative x is going to be a positive number. So over here, when we take the negative logarithm, as in the logarithm of negative x, we are in fact taking the logarithm of positive number, so there's nothing wrong here. What do we get on the right side? Well, here what we have is the natural logarithm of negative x, which I could say as the derivative of natural logarithm of u taken with respect to u times du by dx, where u is equal to negative x. So then, given this case, we can see that du by dx would be equal to negative 1, and the derivative of the natural logarithm of u with respect to u would be 1 divided by u. So therefore, the derivative of the logarithm of negative x taken with respect to x in this case would be 1 divided by u, which is going to be 1 divided by negative x times negative 1. So therefore, here we have that for x's less than 0, if we consider the derivative of the logarithm of negative x with respect to x, we simply get 1 divided by negative x times negative 1, which is going to be 1 divided by x. Therefore, in this case, it appears that the integral of 1 divided by x dx is equal to the natural logarithm of negative x's plus c for the x's which are less than 0. We combine these two cases and we write this in a common form, and we can see here when x is greater than 0, we have the logarithm of x. When x is less than 0, we have the negative logarithm of x. Therefore, overall, we take the absolute value and we say that the integral of 1 divided by x taken with respect to x is going to be equal to the logarithm of the absolute value of x plus c. We can see that all works out. When x is positive, the absolute value of x is going to be x, so therefore the logarithm of the absolute value of x is simply going to be the logarithm of x. And when x is negative, the logarithm of the absolute value of x is going to be the logarithm of negative x, which we can see the derivative of the logarithm of negative x is equal to 1 divided by x. So in both cases, it works out. Therefore, what we write is that the integral of 1 divided by x with respect to x, or the case where we have x to the power of n, where n is going to be negative 1, we write it as the natural logarithm of the absolute value of x plus c. Here, the absolute value of x is here to combat the fact that when we have positive x's, we have one result, when we have negative x's, we have one result, but these two results can be written in a common format as the logarithm of the absolute value of x. So therefore, the integral of 1 divided by x dx is equal to the logarithm of the absolute value of x plus c. The reason for the absolute value is that when x is negative, we have one behavior, and when x is positive, we have another behavior. This, however, is still not defined for x equals 0. So we still need x not equal to 0. At x is not equal to 0, we're taking the logarithm of 0, which we cannot do. Another set of common logarithms comes from the trigonometric functions. And I'm going to list them out really quick, and we're going to write their antiderivatives as our answers. What we know from derivatives is that the derivative of sine x, the derivative of sine x with respect to x is the cosine of x, and we know the derivative of the cosine of x with respect to x is the negative sine of x. We know that the derivative of the tangent of x with respect to x is the secant squared of x. We know that the derivative of the cotangent of x, so cot x with respect to x, is negative cosecant squared of x, cosecant squared of x. We know that the derivative of the cosecant of x with respect to x is going to be the negative cosecant of x times the cotangent of x. And we know finally that the derivative of the secant of x with respect to x is equal to the secant of x times the tangent of x. We know these derivatives. What we're going to be doing now to give ourselves some simple integrals is going to be taking these and turning them around to give us an antiderivative form. Here we can see the derivative of sine x is equal to cos x. Therefore, the integral of cos x with respect to x is going to be the value of sine x plus, of course, c. The reason for c, as we discussed above, is that a large family of functions exists whose derivative is equal to the cosine of x. When we take the sine of x plus c and we take its derivative for any c element of the real numbers, we will be getting the derivative as the cosine of x. Similarly, from the second relationship, we can see the derivative of cosine of x is going to be equal to negative sine of x. Therefore, we can write using our antiderivative law that the integral of the negative sine of x taken with respect to x is going to be the cosine of x plus c. However, this is not usually what we do. Usually, we take this negative 1, we take it out and to the right side, and we write instead of this that the integral of, instead of the negative sine of x, we just write the integral of the sine of x, and we say that the integral of the sine of x is equal to the negative cosine of x, and here putting minus c would be the same as putting plus c, because c can be any real number. So here I can keep the plus c as it is and write that the integral of the sine of x with respect to x is the negative cosine of x plus c, where c is some arbitrary constant. So now we've eliminated these two. Let's now consider the rest of them. For this thing, we have that the derivative of tan of x dx is going to be secant squared of x. Therefore, I can easily write that the integral of secant squared of x with respect to x is going to be the tangent of x, and again, since we have the constant of integration, we need to add the plus c. Similarly, for these three as well, we can write similar equations. I'm going to cut the first three because we're done with them. Let's now take the second three down and write their integral formats. For the first thing, we have that the derivative of the cosecant of x with respect to x is going to be the negative cosecant of x times the cotangent of x. I'm actually going to take this negative to the other side and write that the integral of the cosecant of x times the cotangent of x taken with respect to x is going to be equal to the negative cosecant of x plus c. Similarly, for the secant of x, we know that the derivative of the secant of x is the secant of x times the tangent of x. Therefore, the integral of the secant of x times the tangent of x taken with respect to x is going to be equal to, and over here on the right side what we have is simply the secant of x plus c. And finally, for the cotangent of x, we have that the derivative of the cotangent of x is the negative cosecant squared of x. We're going to take the negative to the other side and write instead that the integral of cosecant squared of x taken with respect to x is going to be, taking the negative to the other side, we have the negative cotangent of x and then of course plus c. These are some common integrals that we have. These set of integrals were derived from the 6 trigonometric function derivatives that we found previously. We used the concept of taking the antiderivative in order to find these indefinite integrals. So therefore the integral of sine x is negative cosine of x plus c, the integral of cosine of x is sine x plus c, the integral of secant squared of x is tan of x plus c, the integral of cosecant of x times the cotangent of x is going to be negative cosec of x plus c, the integral of secant of x times the tangent of x with respect to x is going to be the secant of x plus c, and finally the integral of the cosecant squared of x taken with respect to x is going to be the negative cotangent of x plus c. We're going to be adding one more simple integral to this, and that's going to be the integral of e to the power of x. We know that e to the power of x is a special function, and is special in the sense that its derivative, the derivative of e to the power of x, is itself. Therefore, if we take this expression and we turn it into an antiderivative, we can see that what we would get is that the integral of this thing, the integral of e to the power of x taken with respect to x, would be the internal function which is also e to the power of x plus c. So therefore, the integral of e to the power of x with respect to x is e to the power of x plus c, where c is some kind of arbitrary constant. So then, that's that for our simple integrals. All of these simple integrals were obtained by using the antiderivative idea on simple derivatives that we had found previously. Before we continue to the next lesson, let's do a couple of simple examples. For example number 1, we have the integral of x plus 1 whole thing squared dx. So then, what we're going to do here to simplify this thing is first expand this x plus 1 whole thing squared. When we expand it, we're going to get the integral of x squared plus 2x plus 1 dx. Now then here we can see we have a bunch of terms added together. Therefore, integrating the bunch of terms should be the same as integrating each term individually and then adding them all together. For the first part, we have x squared. We know that when we have x to the power of n, when we integrate it, we get x to the power of n plus 1 divided by n plus 1. Therefore, this x squared should give us an x to the power of 2 plus 1, as in x to the power of 3 divided by 3. Plus, the next term here is 2x. So we have 2 times an x. We'll take the 2 factor out and then take the integral of x. When we consider x by the same logic, x is x to the power of 1. When we integrate it, we get x to the power of 1 plus 1 or x to the power of 2 divided by 2. So therefore, the 2x gives us x to the power of 2 divided by 2. And then plus, here we have the integral of 1. The integral of 1 could be thought of as the integral of 1 times x to the power of 0. And here, x to the power of 0's integral is going to be x to the power of 0 plus 1 or x to the power of 1 divided by 0 plus 1 or divided by 1. So therefore, what we have here is 1 times x or just x. Now we're not done here. Recall, since we have an integral, we must put the plus c to indicate that we have some other constant. We don't know what it is. It could be anything. But we know that there is a constant that we have to add. We haven't found it yet. We don't know how to find it. We just know that it's there. So we add the plus c. If you want, you can write down here where c is an arbitrary constant. Simplifying things a little bit, we can see we can cut this 2 and 2. And writing that as a final answer, we can write 1/3 x cubed plus x squared plus x plus c as our final answer. So then, the integral of x plus 1 whole thing squared is going to be 1/3 x cubed plus x squared plus x plus c. Moving on to the next one. In the next one, we again have sum of terms and we have different terms this time. Over here, we have the integral of 3 times sine x plus 1 divided by x plus 2 divided by x squared, all integrated dx. So then here, this is going to be the sum of each of these integrated separately. For the first one, we have a constant times sine of x. We know that when you have a constant times a function, we can take it out. So this is 3 multiplied by the integral of sine of x. The integral of sine of x, as we found above, is the negative cosine of x. So we'll write here negative cosine of x. Plus, here we have 1 divided by x. We know the integral of 1 divided by x is the natural logarithm of the absolute value of x, as we proved above. Therefore, here we must have the natural logarithm of the absolute value of x. Plus, for this part, we have a constant of 2. So we can put that as 2 multiplied by, and then here we have a 1 divided by x squared. 1 divided by x squared could be written as x to the power of negative 2. Since this power is not negative 1, as we saw above, we can use our rule. Our rule for integral says that x to the power of n turns into x to the power of n plus 1 divided by n plus 1. Therefore, for this guy, we have x to the power of minus 2, therefore he turns into x to the power of minus 2 plus 1 divided by minus 2 plus 1, or x to the power of 1, negative 1 divided by negative 1, as in negative x to the power of 1. So here we have a negative x to the power of negative 1, which I'm going to write in the next line as 1 divided by x. And of course, when we have an integral, we must have the constant of integration. Therefore, here we need to add plus c. Let's now simplify things a little bit and give our final answer. Simplifying this first term, we have 3 times negative cosine of x, which I'm going to write as negative 3 cosine of x. The natural logarithm of the absolute value of x can remain as it is. And here, this 2 times the negative x to the power of negative 1, I'm going to write as negative 2 divided by x to the power of 1. So negative 2 divided by x and plus c. This right here is our final answer of question number 2. For question number 3, we have a little something different. Here we have that capital F of x is equal to this integral here, and we also have that capital F of x evaluated at x equals pi by 4 is equal to 2. Using these two elements of information, we are going to be finding what the function f of x actually is. From the first expression, we can say that f of x is equal to the integral of 1 plus the cosine squared of x divided by, and to simplify this thing, I'm actually going to use an identity that we proved earlier, a very famous identity, very simple identity. If you haven't seen that video, click this video on the top right here. It is the identity that sine squared of x plus cosine squared of x is equal to 1 for any x. Therefore, that means that 1 minus the cosine squared of x is equal to sine squared of x. So here this is equal to sine squared of x all integrated dx. The next step we are going to do is to write this thing in a different form. We know that cosine of x divided by sine of x is cotangent of x. That's how it's defined. So then, therefore, cosine squared of x divided by sine squared of x must be equal to the cotangent squared of x. And this all needs to be integrated dx. Now for our next step, we are going to be using another trigonometric identity. Here we know that given sine squared x plus cosine squared x equal to 1, we can divide everything by sine squared of x. Here divide this thing by sine squared of x. We can divide this thing by sine squared of x. And we can divide this thing by sine squared of x. And the first part will give us 1. The second part will give us cotangent squared of x. And the last part will give us cosecant squared of x. Therefore, 1 plus the cotangent squared of x is equal to the cosecant squared of x. So here I'm going to replace 1 plus the cotangent squared of x with cosecant squared of x integrated dx. Now going up here, recall that we had that the integral of cosecant squared of x is equal to negative cotangent x plus c. We derived that from earlier. Now then, using that thing here, we can say that the integral of cosecant squared of x dx is going to be equal to negative cotangent of x plus c, where c is an arbitrary constant. Therefore, our function capital F of x is equal to negative cotangent of x plus c. However, we also know that f of pi by 4 is equal to 2. So therefore, we know that f of pi by 4 is equal to 2. And we can substitute f of pi by 4 into this thing here. We know that x is pi by 4. Therefore, here, this negative cotangent of x is going to be negative cotangent of pi by 4. As for this plus c, the plus c is going to remain as it is because plus c is a constant relative to x. So here we have plus c. Now then, we know that the cotangent of pi by 4 is equal to 1. So therefore, the negative cotangent of pi by 4 is equal to negative 1. So from this, we can get that negative 1 plus c is equal to 2. Therefore, c is equal to 3. Therefore, resubstituting that back into our expression for f of x, we can now say that capital F of x is equal to the negative cotangent of x plus 3. Hence, this is our final answer. So here I wanted to illustrate to you how we could actually find the value of the constant c given that we knew a particular value of a function at some particular point. So then that's enough examples for now. Let's now go to our next theory. The next theory we are going to be discussing is called the fundamental theorem of calculus. It's a very important theory in calculus and it allows us to relate integration to continuous summation and find the area under curves and such. We can use it to find areas, volumes, and so on. And for single variable functions, we can use integration to relate the idea of the integral of a function to the area between a function's graph and the x-axis. So then, to prove this, we are going to do something as follows. This is not necessarily the most standard way to prove this, but it's one way to prove it. Let's suppose that this is the graph of y equals f of x. So this curve here is f of x. And let's suppose that we have another function called the capital F of x, and this function finds the assigned area between the graph of f of x and the x-axis, starting from an arbitrary value of x and going upward until a given value of x. What I mean by signed area is that area under the x-axis like this would be considered as negative area, and area above the curve like this would be considered as positive area. Let's suppose capital F of x gives us such an area. Let's consider in this case I marked out 2 points, the point at x equals a and the point at x equals b. Let's consider what capital F of a would be. So then, starting from this arbitrary point which we have purposefully not marked, we are going to have to consider the area under the curve from that arbitrary point up to x equals a. So what we need to do is start coloring in like this, from this point up until we reach the point at which x is equal to a. So therefore this shaded region in blue is the area which is correspond to the value of capital F of a. Now let's consider what capital F of b would be. Considering this definition of capital F of x, capital F of b would be the area under the curve starting from this arbitrary point which we have not marked all the way up to the values at which x is equal to b. So therefore this red shaded area here is what capital F of b would represent. Now then, suppose we want to find the area under the curve between x equals a and x equals b. Let's suppose this area is called capital A. Well, considering what we have here, the red region capital F of b encompasses this whole entire area which we have drawn here, and capital F of a encompasses only this bit and this bit. We can see that capital A here is the difference of the red area and the blue area. Therefore, capital A, the area between x equals a and x equals b under the function f of x is going to be equal to capital F of b minus capital F of a. This is one idea which we are going to be using later, but for now we are going to understand this idea and save it for later. The next thing we are going to do is consider the derivative of this function which we have defined, capital F of x. We are going to consider the derivative and use that to find a relation between capital F of x and simple f of x. So then, moving down. Supposing that this is the function capital F of x's graph, simple f of x's graph, let's consider what capital F of x would be. Let's suppose that we count up to this point here. This point here which we are going to call, let's call it P. And let's suppose we consider f of capital F of P and capital F of P plus dx. So let's consider moving forward a distance of dx. Well, from our arbitrary point, counting upward, this right here would be the area of f of p. And then counting upward from our arbitrary point, this right here which I'm shading in would be the area of f of p plus delta x. Capital F of p plus delta x would be that area there. Therefore, this area in the middle, this area under the curve here, this area would be capital F of p plus dx minus capital F of p. This is the value representing this little area here. What we're now going to do is to consider something like this. Let's draw a horizontal line from this point here of f of p, simple f of p, to the right like this. At this point, the height here, this y-axis level, is going to be simple f of p. Here we can see the area is approximately the area of this rectangle. We have the area of this large rectangle here and this small triangle over here. Let's write out their area separately. For the large rectangle, let's draw out its area in orange, and for the small triangle, let's shade its area in pink. Considering its orange area, let's call this orange area A1 and let's call the pink area A2. So here we have A2. First off, what we know is that A1 plus A2 added together is equal to this other expression for the total area under the curve. So this is going to be equal to f of p plus dx minus f of p, and that is our first equation. The second equations that we're going to be constructing are the equations for the areas A1 and A2. Considering A1 is the area of this rectangle that we've drawn here. This area of this rectangle is going to be one of the side lengths, which is dx, times its other side length, which is f of p. So therefore, area A1 is equal to f of p times dx. How about area 2? Well, considering area 2 is going to be a triangle approximately. It's not exactly because it's somewhat curved, but it's approximately the same as a triangle. And considering the y-axis is involved, this height here is going to be the value of simple f of x at x equals p plus dx. This is going to be f of p plus dx. So then we have a height here of f of p plus dx minus f of p. As for the width is dx. So therefore, the area number 2 is approximately equal to the area, which is half into base into height. So half into base is dx into height, which is f of p plus dx minus f of p. Now then, let's consider each of these equations and consider what happens as we take the limit as dx approaches 0. As dx approaches 0, here we have just a dx, this thing is going to go to 0. However, this f of p is a constant. Considering the other things, this part here, this is going to go to 0, so therefore this is going to approach f of p minus f of p, so this thing is going to approach 0. As for this thing, here not only is this thing approaching 0 as we have dx directly, and as we take the limit as dx approaches 0, dx is going to approach 0, but this thing is also going to approach 0. Here we can see within this expression there are two things that are approaching 0. This is approaching 0 and this is approaching 0. As for the other expressions, this is approaching 0, only this part's approaching 0, and over here only this whole thing is approaching 0. Let's now substitute each of these a1 and a2's equations into here and consider the entire limit as dx approaches 0. Considering the entire limit as dx approaches 0, what we have here is that we have f of p times dx plus half times f of p plus dx minus f of p times dx, so we can close this bracket and say times dx, being equal to this stuff on the right here, which is going to be f of p plus dx minus f of p. So I'm going to rewrite this nicely in this second line. I wrote this just so you could copy it down. Now we're going to rewrite this and apply a limit. What we're going to do is apply the limit as dx approaches 0 to f of p times dx plus half times f of p plus dx minus f of p times dx, and this is going to be equal to the limit as dx approaches 0 of f of p plus dx minus capital F of p. Now then, what we're going to do here first is divide everything by dx. Now here, since dx is only approaching 0 and it's not equal to 0, we can totally do this. Doing this here, we can see on the left side we have a dx here and a dx here which get cancelled, and on the right side we just have to add a divide by dx. So therefore what we get is here the limit as dx approaches 0 of, when we divide by dx, this is going to be just f of p, plus this thing when we divide by dx is going to be half times f of p plus dx minus f of p. Since now we have divided by dx, this part's gone, and on the right side this is going to be equal to the limit as dx approaches 0 of f of p plus dx minus capital F of p all divided by dx. Now then, let's consider what we have here. On the right side, if you watch the video on derivatives or you have some knowledge of derivatives, you can see Here we have f of p plus dx minus f of p divided by dx, which is exactly the definition of the derivative of capital F of x evaluated at p. So therefore on the right side what we have here is the derivative of f, which I'm going to write as f prime, capital F prime, evaluated at p. On the left side, considering what we have, f of p is a constant with respect to dx, so therefore we can actually take it out of the limit. So here we have just f of p, and for the other thing, here we have half times this thing right here, so this is going to be plus half times f of p plus dx, which is going to be f of p, since dx is approaching 0, minus f of p. Considering what we have here, we have that f of p plus 0, because this here we can see f of p minus f of p here, this is going to be 0, is equal to capital F prime of p. This is the relationship we wanted to find. We wanted to show that the function whose graph we drew is equal to the function that gives us the area's derivative evaluated at that same point. So therefore, if the function of the graph is equal to the derivative of the area function, then the area function must be the integral of the graph function. In fact, we have a special notation for this using the integration sign. We write that if we want to find the area between any two points, let's say x equals a and x equals b like we did here, if we want to find this area a using integration, instead of having to first find f of x and then write that evaluated at b minus that evaluated at a, we could simply write using one notation that the area a is equal to the integral from a to b of f of x dx. This is what we call a definite integral. The idea here is that we first integrate f of x with respect to x and find the function corresponding to that, i.e. the function that when you take its derivative, you get f of x. And then after finding that function, we substitute the value of b, subtract from that the value substituted at a, i.e. we find the value of the function at b and then subtract from that the value of the function at a. So therefore, what this notation means is that first we have to find the function capital F of x corresponding to simple f of x, whereas in when we take the derivative of capital F of x, we get simple f of x, and then we evaluated it at b and then evaluate at a, subtract the two and get our answer. This is the idea of this notation here. The notation is the starting point, the ending point, what function we are integrating and with respect to what variable. When we have all of this is essentially asking, if I take some function capital F of x and I take its derivative with respect to this variable, I should get simple f of x. Given that I get that, I want to evaluate f at b, subtract from that the value at a and give that as our final answer for the area. Now then, let's do this for a couple of simple examples and carry on to our next idea. Before continuing to the next part, let's do a few examples to familiarize yourself with this idea. Here I have a graph of y equals x cubed plus x squared minus 2x plus 1. And suppose we want to find the area between this curve and the x-axis from x equals negative 2 up to x equals 2. Therefore, we want to find this shaded area right here. Let's suppose we call this area capital A. From the theory we just learned, we know that capital A is going to be equal to the integral starting from negative 2 and ending at 2. So therefore, starting at negative 2, ending at 2, of the function which is going to be x cubed plus x squared minus 2x plus 1. So we're going to have x cubed plus x squared minus 2x plus 1 integrated with respect to x. Now then, if we take the normal indefinite integral of this thing's normal indefinite integral is going to be the first term's integral, which is going to be x to the power of 3 plus 1 divided by 3 plus 1, x to the power of 4 over 4, plus the next one's integral, which is going to be x to the power of 2 plus 1 divided by 2 plus 1, or x to the power of 3 over 3, and then minus 2 times this thing's integral, so minus 2 times x's integral, which is going to be x to the power of 2 over 2, and then plus 1's integral, which is going to be x, so plus x and plus c. We need to evaluate this function at x equals negative 2 and x equals 2 and subtract the two from each other. Before we do that, however, I'm going to point out a certain thing. When we do this subtraction in order to find the area, notice that this term here has a constant on the inside of it in the form of plus c. This term also has a constant inside of it in the form of plus c. And then, since this plus c is independent of a and b, as in independent of x, both of these have the same plus c. And when we subtract them, both of these are going to cancel out, no matter what the c actually is. So the constant c could be anything, it is anyway going to be cancelled out. Due to this, when we take the limits, when we do capital F of 2 and subtract capital F of negative 2 here, we can just ignore the plus c part. Here this is capital F of x. We can ignore the plus c part when we are doing definite integration because it's going to be cancelled out anyway. So then, ignoring that part, what we need to do here is evaluate this function capital F of x at 2 and negative 2. In practice, when we are doing this, we usually write the function on the inside of a big bracket like this. Sometimes you put like a line like this instead. I like the bracket method. Here we write the upper limit, here we write the lower limit, and on the inside we write the function that we are evaluating. So then, the indefinite integral of this thing is going to be x to the power of 4 divided by 4 plus x to the power of 3 divided by 3, and then minus 2 times x to the power of 2 divided by 2, and then plus x. This is the function we have to evaluate between 2 and negative 2. Evaluating this out, we get 2 to the power of 4 divided by 4 plus 2 to the power of 3 divided by 3 plus, actually minus 2, actually we can cut this 2 and this 2, so just minus this thing squared, so minus 2 squared and then plus 2. This is the first limit. We have to subtract from this the values at negative 2. So therefore from this we have to subtract, substituting negative 2 into here, we have negative 2 to the power of 4 over 4 and then plus negative 2 cubed over 3 and minus, here cutting the negative 2, so all we have here is negative 2 squared and plus negative 2, so I'll just put that as minus 2. Now then, we have to evaluate this thing. On the left hand side we have 2 to the power of 4 divided by 4, which is going to be 16 divided by 4, which is going to be 4, so here we have 4. This bit is going to be 8 divided by 3, so plus 8 divided by 3. This part is going to be 4, so negative 4. And this part is going to be 2, so plus 2. From that we have to subtract this thing on the right here. Negative 2 to the power of 4 is going to be 16, so here we have 16 divided by 4. And then this part here is going to be negative 8, so negative 8 divided by 3. This part here is going to be negative 4, so minus 4. This part here is going to be negative 2, so minus 2. Now then, seeing as what we have here is 16 divided by 4 and here we have a 4, we can cancel these two out inside of this bracket. Similarly, this 4 and minus 4 can cancel out inside of this bracket. So what we have here is 8 divided by 3 plus 2 minus negative 8 divided by 3 minus 2. You can see here we have 8 divided by 3 plus 2 minus negative 8 divided by 3 is plus 8 divided by 3 and minus negative 2 is plus 2. So then what we have here is 2 8 divided by 3s and 2 2s. So we can write this as 16 divided by 3 plus 2 2s, so plus 4. We could take this under a common denominator and we could say this is divided by 3 and on top 3 times 4 is 12, 12 plus 16 is going to be 28. So therefore the area under this curve, y equals x cubed plus x squared minus 2x plus 1 from x equals negative 2 up to x equals 2 is going to be 28 over 3. This is how we use integration, definite integration, in order to find the area under curves. Let's do one more. Let's do the integral of sin x as a simple example. Moving away from our more complicated examples, taking a rather simple example, let's try and find the area in a sine curve from x equals 0 up to x equals pi. Quite a simple thing that we want to find here. We want to find basically this area here. So then, here at the start we have 0, here at the end we have pi, and therefore what we are looking for here is the integral of the sine of x. So we can say that this is sine of x, or y equals sine of x. We are looking for the area, which I'll actually label the area as well. We'll label the area as a. The area a is equal to the integral starting from 0 and ending at pi, so starting from 0 ending at pi, of the sine of x dx. Now then, this thing's quite simple. All we have to do is evaluate sine of x's integral, which we know to be negative cosine of x. So we have to find the limits of negative cosine of x from 0 up to pi. Basically, we need to substitute pi into this equation, then we need to substitute 0 and subtract the 2. So then, what we have here is going to be, first off, negative cosine of pi, and from that we need to subtract the negative cosine of 0. This is our answer. Now then, we know that the cosine of pi is equal to negative 1. Substituting that in, we get negative 1 minus, and we know that the cosine of 0 is going to be 1. So therefore we have minus 1. Now then, evaluating all of this, we can see the negative 1 is going to be 1, and the negative 1 is also going to be 1. So we have 1 plus 1, which is 2. Therefore, the area under this function from here to here, basically the area of this kind of camel's hump shaped curve of sine x is equal to 2. Hence, we have our answer. So in order to end this video, let's discuss some theorems on definite integrals. One of the theorems on definite integrals is that if you integrate any function f of x with respect to x, from a up to a, as in the same limit is on top as on bottom, effectively what we are looking for is f of a minus capital F of a, which is going to be 0. Therefore, integrating a function from a certain value up to that same value is going to give you 0. That's one of the theorems. Another theorem has to do with continuity. If we have that some value c is in between a and b, such as this, then if we take the integral from a to b of f of x with respect to x, it would be the same as integrating a up to c of f of x and then integrating the rest of it, which is the integral from c up to b of f of x dx. Now here, of course, f of x needs to be fully integrable along that entire range, but if that's the case, you can in fact do this operation here. The next thing is going to be the fact that if f of x is less than or equal to g of x for x being an element of the set going up from a up to b, if this is the case, as in for every value of x in between a and b, f of x is less than or equal to g of x, it means that the integral from a to b of f of x dx is also going to be less than or equal to the integral from a to b of g of x dx, i.e. if at every single value f of x is smaller or equal to g of x, then across all of the values f of x's area that we add up together is of course going to be lower than the values that we add up for g of x. The next theorem is going to be grabbing on this theorem and saying that if f of x is bounded in between two values, let's say a minimum value and a maximum value, therefore what we mean here is that f of x is somewhere in between these two values, then the integral from a to b of f of x dx is going to be somewhere in between the values of m's integral, which is going to be, since m is a constant, is going to be mx evaluated from a to b, which is going to be m or times b minus a. It's going to be less than or equal to m, capital M, times b minus a, where m, capital M here is the maximum value that f of x can have within a certain range, and simple m is the value minimum that f of x can have. And here this needs to be for all x's within the range from a to b. So effectively we can bound the area of a function, area under a function, between a maximum and a minimum using this concept here. There are other concepts relating to definite and indefinite integrals that we need to talk about, other rules and other things that we can do to these things. However, those are going to be covered in the second part of this video. So that's it for this video. Thank you for watching and goodbye.